Hello everyone and welcome to another lecture. Today we are going to talk about change of basis and similarity transformations. So in our discussions we took the vectors written in direct notation. Let's say I have a vector and this can be written as sum over I, the components and the basis, let's say. So since we are summing over this I, let's call this basis as I. This vector V, the information that this vector encodes is coordinate / basis independent. However, the components and the basis, they can change. So they are basis dependent. But the total information that the vector will encode will be basis independent. So you can write this vector V in another basis in a similar fashion. Let's call this I primes and we denote our component as primes, and so are the bases. So this is how we can write it, and this is equals to just Vi I basis. And let's say there is some transformation which we denote with S. So there is some transformation S that takes us from basis I to I prime, and mathematically we will denote this as the following. Obviously you can work in the component notation as well, but let's just keep this thing over here. So what does this tell us? That is this equation over here, call it equation 1. And what does this tell us about the components, right? So we agree on the fact that the vector itself should be coordinate independent or the basis independent thing. So using this equation over here, we can actually draw a relation of the components as well between the components V prime and V. So how do we do that? Let's try to see it. So we have our summation over I, Vi I is equals to sum over I prime, and you have Vi prime and you will have I prime, right? But this I prime is related with I through equation 1. So now we will use equation 1. So using equation 1 we will get the following, that is Vi prime, there will be a S and there will be a I, and here on the left hand side you will have I, Vi I. Now they look almost the same, however the bases are the same, so the components should be equal as well. And instead of summing over I primes, now the sum will be changed and it will be going to just I. So let me get rid of this prime over here, and comparing the left hand side and then right hand side, we can write Vi is equals to S Vi prime, because these S are when you think in terms of the column matrix, that's how you should write it. That is, this is still in the component notation. So if you want to use the bar notation to denote a column of the components, this will be just S V bar prime. This is the proper matrix equation. And here since this looks like a component notation, you can always add this sum over, let's say I prime and I, something like this. So it's totally a matter of choice what you want to write. but either way, this means this is the punchline, that this is how the components are getting transformed. So you can see that the components v prime will be actually related to S inverse first and then a v. So the components transform in the opposite way the vectors, the basis vector transforms, because the basis vectors transformed in a manner like this, and the components are using the S inverse, assuming it exists. So using this, we are going to see something called a similarity transformation, and you can easily verify that the vector itself will be invariant under this kind of transformation. So let's try to now see what is a similarity transformation. And this S matrices will correspond to the similarity transformation. So let's consider an operator equation that we are most familiar with. That is, let's say y, and it is related with some x. This is one operator equation, and since this is an operator equation, this will be basis independent. So let's say I'm working in another basis, so let's call this basis 1, or non-prime basis, let's say non-prime basis, and this will be the equation for the primed basis. And note that I am also giving a prime over the operator A, because the elements of the operator, if you think in terms of matrix, they are basis dependent. So that's what I'm indicating with the prime over here. And these two equations, that is equation itself, the whole thing is basis independent, both of them. And since we are considering a similarity transformation, that is, we are considering a change of basis, what we want to do now is the following, that is, we are trying to relate A prime with A. So let me write our goal. We want to relate A prime and A with the help of S, right? Okay, so what I'm going to do now is that I'm going to say that, like these components over here, because you can obviously decompose them, these x's, into the components, and these x primes will be related to x via S inverse x, right? Think of this in terms of components. If the ket notation confuses you, don't worry about it. You can just easily get rid of this ket notation and write it as the following. Because each of these kets, let's say y prime, so let's call this y1 prime, y2 prime, and so on. So that's why I'm telling that you are relating this transformation with the components, not the basis itself. Alright, so if you do that, let's get rid of our ket notation so that you guys don't get confused. So this is how these things look like, and they have components inside them. And since each of this, and what will happen is that each of the components within this x prime, that is, if you write x prime as, let's say, x1 prime, x2 prime, x3 prime, this will be just some S matrix, and here you'll have, S inverse 1, x3 dot x4 . So this is how they are related, and I'm going to use this fact. So if you write in a matrix manner, this is just this over here. So you have y prime equals to, it should be a prime over here, a prime, and instead of x prime, now let's write S inverse x, right? Similarly, y has its components like this as well, like this. That is, y prime will be y1 prime, y2 prime, yn prime, which will be related with some S matrix, and S inverse 1 and y1, y2 and y3 and so on. So here you will have a S inverse 1y, and this equation. Then what you need to do, you just need to multiply both sides with S on the left. So if you do that, this guy will become y. You will have S over here, the operator a over here, sorry, not a prime, and S inverse 1 over here, and x is over here. So note that we are calling these operator equations are basis independent, so they mean the same thing. So if you now compare, this is coming in terms of y on x. So if you compare this equation, let's call this equation 2. So compare 2 with y equals to ax, and if you compare them, you can easily see that we are getting a equals to s a prime s inverse 1, or similarly a prime would be a s inverse 1 on right and s on the left. So this is what is known as a similarity transformation. This is our similarity transformation. And note that this kind of looks like something we have seen before, right? When we talked about something called a Heisenberg picture. In our earlier lectures, we saw that if you have a Hermitian operator and you have these unitary operators, and if you change them like this, the underlying physics remains invariant. And this is the most general case, the similarity transformation itself. And a special case is this unitary transformation, where the similar matrices, that is S, are actually unitary matrices, and the underlying physics or the underlying physical information will be same under this kind of transformations, because it's just a change of basis, and whatever physical information we have is not dependent on the basis itself. So you can easily verify that, let's say you have an operator, let's take A again. So under this similarity transformation, the trace, let's call it TR, the determinant, the eigenvalues, all are invariant. And what does that mean? That means the trace, the determinant, the eigenvalues, all of them are not dependent on the basis. So that's why they are important to us in physics, and that's why we say the physics is invariant under a similarity transformation. In fact, in the next lecture we will see how we can use this similarity transformation to make a matrix diagonal, and that will help us in a very long run, not only to compute functions of matrices, but also to get the trace, the determinant, and many other complicated things that might seem a bit complicated at first, but using the similarity transformation, that is the change of basis itself, we can make our lives really easy and the calculations are a lot simpler. So this will be it for today, and I'll see you guys in the next lecture. Thank you.